Welcome to the first Neuro Talk Evening. You people might wonder why there's this post-edit and also why there's nobody else visible except for me. This is due to some problems we had with recording. Sadly, the first few minutes, which was the introduction, were corrupted, and therefore we're had to do this post-edit. So sorry for that. We're definitely trying to fix that next time. But yeah, let's come back. My name is Sebastian. I'm at the moment in charge of the organization of the Neuro Talk Evenings from our network. So if you have any suggestions or people you're in contact with and you would really like to see at this event, just let us know. Feel free to message us at any given time. But back to the first Neuro Talk Evening topic, which was what does the primary visual cortex, especially V1, do? And our guest was Professor Zhaoping. She is widely known for her V1 saliency hypothesis, a theory that suggests that V1 is guiding attention through creating a so-called saliency map of the visual perceived stimuli. In addition to her expertise in neuroscience, she also has a PhD in physics from Caltech, and at the moment she's working at the Max Planck Institute in Tübingen, where she is the head of the Department of Sensory and Sensomotor Systems. That all not being enough, she's also an author and providing lots of public education through her YouTube channel, which she's keeping alive on a regular basis for more than over 10 years right now. And yeah, so let's come back to the topic. We all can tell and we all have experienced that vision is the most present, most dominant, and most important perception in our day-to-day life as a human being. But if you really think about it, how does one accomplish this incredible art of perceiving visual information and also selecting visual information? This is where the key role of V1 comes in, and this is also the point where I would like to hand over to Professor Lee. So thank you and have a nice evening.
Thank you very much for inviting me. I feel very honored to be the first one, but also feel a little bit pressured that, this is, trying to see how it works. If it works well, then we hopefully can attract more people into that network. But I think the science is going to be fun. So, yes, and I'm particularly very pleased with the communication with Sebastian and regarding a lot of how it works, what this network is for. It's for students, and also students have already asked a lot of the questions before the presentation. And that means I have the opportunity to already know what you might be interested, so therefore I have adjusted my presentation accordingly. Feel free to ask me questions additionally, even if just something you never even put in the list. Suddenly there's a new question, because it's really for communication. Yeah, you can hear me well, everybody? Yeah, great, thank you. So let's start. So what does V1 do? Okay, people may feel like, isn't this something that we already know? So let me see if the animation works. Yeah. So people may feel this is something already known in a textbook. Yeah. Huber and Wiesel told us more than half a century ago how V1 actually maps visual input into its neural responses. So for example, here is a neuron that prefers one particular orientation of the bar, so have a lot of responses to this orientation, but very little response to that orientation. And so that's known a long time ago. So what is the question? The question is really, there is a second part to this question. What does V1 do behaviorally? Not just how it maps visual input to neural responses, but from neural responses to behavior. Traditionally, it is thought that V1 doesn't do anything particularly important for behavior. Yeah, it is like a back office job for things such as face recognition, memory, attention. All these important jobs are done elsewhere. And this is monkey's brain. And you can see that vision occupies a large part of the brain. All these brain areas colored are devoted exclusively, almost exclusively to vision. That's 50% of the brain. And how much is devoted to V1? It's a very huge part. So therefore, if it's not doing anything important, why is brain devoting such an expensive resource to it? So therefore, what is the functional role of V1? Well, V1 is not the only brain area for which we're asking this question. More than half a century ago, hippocampus, we did not know what is it doing until we have a medical case for a patient named HM, whose brain surgery removed both sides of hippocampus, and then he can no longer have the memory. From this case, we understood that we learned a lesson that hippocampus is for memory. But V1 is larger than hippocampus, at least for primates. Of course, size is not everything. We have these two tiny regions in midbrain. They are so important. Without them, life is not worth living. And so therefore, it's not just the size that matters. It is the computational role. What is V1 doing computationally? We noticed that it only took us about 10 years for us to know to go from retina to V1. Okay, 1953, Kufler found out how retinal ganglion cells transform visual input. And by the 1960s, Hubel and Wiesel have already found a lot about V1. And you might hope that perhaps another 10 years is needed, then we will know V2. And since then, almost 6 of such 10 years passed, and things seem to be much more difficult. So perhaps, well, our assumption about what V1 is doing, that as if it's doing nothing, is not quite correct. So let's go back to the drawing board. What is V1 doing? We can think about what is actually vision. In vision, in fact, we do not see everything that's falling onto the retina. We see only a tiny amount. And this is called an attentional bottleneck. So for example, here are the two images for you to see. Is there any difference between these two images? You have a subjective impression that these two images are so clear that you see everything. If so, you should see the difference between these two images right away. But no, you do not see them right away, yeah? Can you see the difference? Anybody? Raise your hand. 1. Okay. So most people could not see it immediately if they haven't seen this example before, but this is exactly the difference. In one airplane, there is no engine. Another airplane, there's an engine. It turns out that if you have your eye directed to this engine, you could not even tell whether there's an engine there unless you shift your gaze to go look at that. Yeah. And so we actually see very little. We see less than 1% of all the information onto our retina. So what we see mainly is within the attentional spotlight. And then the question is, how do you choose what is the spotlight? And we mainly choose by a gaze shift. So for example, if you fix your gaze on this letter F, you could not actually see this letter N. It's just a few letters away. You have to shift your gaze before you do that, yeah, before you could see the letter. And so in psychology community, people have been asking, where does this bottleneck come from? Somehow 99% of information did not quite come to our awareness. People ask, does this bottleneck happen before or after we recognize the object, before or after the memory, before or after this and that? And these kind of questions really talk about functionally before recognition or after recognition. However, let's ask the question anatomically. Where is it along the visual pathway from the retina to V1 to V2? Where does it start? Yeah, before or after V1, for example. And so about a few years ago, I proposed that it starts right after V1. So that really nails it down. So it says early selection or late selection. This is quite early selection. And this is a hypothesis that's motivated by a lot of evidence backing this theory, which is proposed more than 2 decades ago, that V1 actually builds a saliency map from its input, from which the eye movement is then guided to. So in particular, in this map, you may have the most salient location, second most salient location, and so on. And this map is then downloaded or read out by the subcortical area, superior colliculus, to find the winner location. That means the most salient location to shift your gaze. That's why. And a location in your peripheral visual field with the gaze shift will become in the center of your visual field. Well, let's also pause to define what do you mean by saliency? Saliency map? This is actually means saliency is driven by exogenous visual input, not any endogenous factors such as your goal, your emotion, your prior knowledge, and therefore it's often called bottom-up saliency. And of course, you may have heard of such terms like emotional saliency, semantic saliency, and so on. That's not part of the saliency here. This saliency map is in V1 before you recognize object. Okay. Now you may ask that, well, traditionally it is thought that shifting gaze is controlled by frontal and parietal areas, and these brain areas also project to the superior colliculus, which can project to the brainstem and move the eye muscles. Maybe these, why are you saying it's V1? These are traditionally known to shift gaze. However, these areas, they usually do saccades driven by endogenous factors, such as your prior knowledge that, okay, here's the door, your parent might come into the door or something like that. You have a task looking for your dog or making coffee and things like that, yeah? And so these kind of gaze shifts are task-dependent, goal-dependent, and they are called top-down guided gaze shifts. And we are going to argue that they play a lesser role in guiding gaze shift. Now, why is that? Because these are voluntary guided gaze shifts, and we shift our gaze about 3 times a second. That means within a minute, you shift your gaze about 180 times a minute. However, you typically feel that you only shift your gaze about 5 times a minute or 10 times a minute, right? And only with our textbook learning, we realize we actually shift gaze a lot. So that means a lot of the gaze shift you are not aware. This under the tip of the iceberg. Another brain area, so in a sense, before I talk about another brain area, in a sense that this gaze shift, and you can say which gaze shift is more important. Not only the ones that are not aware is majority, but also the initial gaze shift is before you recognize something. It somehow sets the initial condition for vision, as if it can have a butterfly effect, a little bit flip, and a fluttering of a butterfly wing can make you, affect your life later, quite a lot. That's the idea. And another brain area that projects to superior colliculus that might affect your gaze shift is retina. But you say, well, could retina also make you shift gaze? Well, at least in primates, they don't. So if you lesion V1, you still have the retina project to V1, project to superior colliculus, then the monkey can no longer do any gaze shift, at least for two months. I'm going to come back to this later also. So therefore, with this, you can think about if you do approximation as if V1 is the main player for gaze shift. And if shifting gaze is in order to direct your attention, and therefore attentional bottleneck should start right after V1. For economic reasons, you should not wait until V2, V3, V4, because the longer you hold with lots of information, the more brain resources you have to consume to process this information. So this is an economic argument for bottleneck start right after V1. And so therefore, if V1 is where the bottleneck starts, what does that say about vision? Okay. In particular, after V1, you will have so little information, then you will have difficulty seeing what's going on. This information did not come through for you to recognize. And that's even true for the central visual field. You may wonder, well, is this really a red flower or red apple? And if you could not see clearly, you may go back to V1 before the bottleneck starts to query for additional information that can distinguish between these two possibilities. let's say if you could not distinguish them, you will have this perceptual ambiguity. It could be this or could be that. And to disambiguate, you need more information. And this process is called analysis by synthesis. I'm going to dig in a bit more later. However, because feedback back to V1 is an expensive brain resource, yeah. So for this reason, we only restrict it to within the attentional bottleneck. So this is a hypothesis which is given by this additional theory, which is called central peripheral dichotomy. That means the feedback, one of the component of this theory says the feedback is mainly directed only to the central visual field. So therefore, in this framework, we start with a bottleneck that should start right after V1, motivated by the hypothesis that V1 shift gaze by making a saliency map, and then followed by a consequence with this bottleneck for our visual recognition. At this moment, you should feel very suspicious. This is as if I'm building sandcastles, 3 layers of sandcastles, but this framework, VISH, bottleneck, and CPD is actually built on a solid foundation of primary visual cortex that is discovered by, whose property is discovered by Huber Weasel in its neural responses. So now let me show you what are the experimental evidence for number 1, number 2, and number 3. So let's start with the bottleneck. You say, are you sure the information bottlenecks start right after V1? So what kind of information is lost by V2? Let's ask that question. Okay, the information that's lost by V2 is actually about the eye of origin of visual inputs. So imagine if you only show something to one eye. We human observers cannot tell whether it is shown to the left eye or right eye. However, in V1, you have monocular neurons. For example, some neurons are only responding to visual input to the left eye, some neuron to the right eye. By looking at which neuron is active, you can tell whether it's the left or right eye sees it. However, human observers cannot tell. This is because by V2, all neurons are binocular. So therefore, a neuron can be driven by input to the left eye or right eye. So therefore, the firing, the activity of this neuron cannot tell you whether the input is to the left or right eye. And people have tried to find a way, can we, some people say, yes, I can tell whether it's the left and right eye. If somebody can tell that, it's because there's an artifact. So for example, one of your eye could be a lazy eye, or seeing less well than the other eye, then you can tell just by whether the image looks clear or unclear. But if you remove all these artifacts, human being cannot tell whether input is from the left or right eye. And of course, V2 to V3 or V3 to V4 can have further information reduction, but at least it already started to reduce from V1 to V2. Okay, so that's the case. Now I'm going to show you evidence for number 2 that V1 actually guides your gaze shift. And to show that more convincingly, I'm actually going to show you that this information about which eye sees what that's unavailable to V2 actually can guide your gaze shift. How do you do that? Imagine you make people look for a uniquely oriented bar. Now, even though you may not have seen this airplane engine in that image, this uniquely oriented bar can guide your gaze, see it immediately. So usually observers will find this uniquely oriented bar in a background of uniform oriented bars. Within half a second, they can press button. And this is so even if you put all these bars to one eye only. How do you do that? You can use these stereo goggles people use to see 3D movies to present images only to one eye only. And they can still find it within 1 second. However, if you put one of the non-target bar into the other eye, now, well, what they see is not changed. They still see the same thing. They would not be able to tell. This bar is unique. People cannot tell by their awareness, but your V1 can tell. And what happens? In such a search task, the first gaze shift in majority of the trials in 3 out of 4 trials is directed to that location. Okay, this is especially when these two locations, when one is your target, one is completely not your target, are far away from your initial gaze position. Okay, and often this happens in such a short latency, less than 300 milliseconds, too short even for binocular rivalry to start. Okay, usually observers, they realize that this is not their target, then they make a second gaze shift, then they find their target, they say, okay, I found it. And they were not even aware they just made the first gaze shift. So if you ask observer, you say, well, look, I asked you to find this uniquely ordered bar as quickly as possible. Don't get distracted, but you actually get distracted. They will say, no, I did not get distracted. Immediately I found this bar, I pressed the button. And so you can see that this gaze shift is such an involuntary act they did not know. And so therefore, it's as if this bar is uniquely colored. It's so salient, even though it's not a target, they will attract your gaze to it. But this unique color is only visible to V1 and not visible to their awareness. And we even tested by a control experiment in which they no longer need to find this uniquely ordered bar. All they need to do is to say whether there's any bar in what they see without any cheating, without blinking one eye and keeping one eye open, to say whether there is a bar in a different eye. They don't have to say which bar. You can tell them in 50% of trials, all bars are in the same eye. In 50% of trials, one bar is in a different eye. They could not say whether this trial is the one with a bar in the same eye or not. And this is such a surprising finding, but nevertheless, it's such an important finding that different labs try to replicate it and successfully replicate this finding. Okay, and you may ask, what is the neural mechanism for doing that? It turns out that in V1, they have these recurrent interactions that enable neighboring V1 neurons that are not exactly in the same receptive, having exactly the same receptive field location to interact with each other. And one important interaction is called isosphere suppression. And this can be even modeled in a neural circuit model. But for example, iso-orientation suppression make V1 neurons tune to the same orientation. For example, these orientations for the background bar, they activate V1 neuron tuned to its orientation, and they are tuned to the same orientation, so therefore they suppress each other. This is called iso-orientation suppression. However, this target bar is activating a V1 neuron tuned to a different orientation, and so therefore it's not being suppressed because iso-oriented suppression only suppresses neurons tuned to the same orientation or similar orientation. And so therefore, this neuron is giving an unsuppressed response and other neurons give suppressed response. So therefore, if you have this as a saliency map, this is the most salient location, will then go through superior colliculus to attract your gaze. And if you put one bar to the other eye, now in V1, you also have something called eye of origin suppression, which means neurons tuned to the same eye also suppress each other. So all these left eye bars exciting neurons tuned to the left eye, they will suppress each other. And this bar will excite a V1 neuron tuned to the right eye. It will not get suppressed. Therefore, it will also activate higher. And now you have two locations. One is because escaping the eye of origin suppression, and the other is because escaping iso orientation suppression. And then it's like in this saliency map, you have one most salient and one second most salient. Then a superior colliculus will find a winner. And if this is more activated, then you will find this phenomenon that we find in our psychophysics experiment. So is it a good time to pause? Any questions like to ask, or should I continue?
I just would ask one small question.
Okay.
So in the beginning, you mentioned that if you focus on the letter F, we
Yeah,
couldn't see the letter N later because it is a few letters away, right?
correct.
So my prof at the University of Osnabrück, Professor Gruber, was a part of a study in 2003, I guess, from Müller et al. And colleagues, where they showed that we actually can split the attentional spotlight. So it might be that there are different opinions on that, but I guess it would not be in the same theory, or couldn't be compatible with the same with your theory of we only can look point the spotlight at one location, or
people have tried to test whether we can split attention to different locations. In 1990s, they found that you cannot. If you can, usually it's actually because you're shifting from one location to another so quickly, you thought that you are attending two places at the same time. In fact, you are not.
They used actually steady state responses, and so therefore they tried to impair the switching. So they had the participants watch four symbols, and it flickers, and every time it flickers, the symbol switches. So you see an 8 and 6 and so on, and it's flickering so fast that the people couldn't switch between two locations because there would also there would already be another sign, and they had them to look for two specific locations and say, if there's a 6 and there's an 8, you need to tell us. And for steady state responses in EG, you can, of course, you can see if there is an amplitude increasing or decreasing regarding to attentional focus on one's stimulus or not. And so in that experiment, I think they showed that there was an attentional focus on 1 and 3, and 2 wasn't focused. And even it was in between. But I
I would
might
like to
be
see
wrong.
the paper. Yeah, they'll be very interesting. I'm not sure, but let's do experiment right now, shall we? Okay.
Of course,
So
sure.
fix your gaze on this letter I. Trying to see this letter T. Can you do that? Difficult, isn't it? You can say maybe I can also see the letter S, maybe also letter O, but to see something far away, it is actually difficult. And later on, I'll give you another example. Okay, so it is quite difficult. Yeah, let's and so this then very good. Thank you very much, Sebastian, for asking this. Very good. And so with this like a very big signature of V1 guiding attention, guiding gaze shift, then this is then followed up by testing in monkeys. This is a collaboration with my collaborator Wu Li, who is an expert on monkey physiology, especially V1. So in this case, we actually let monkey look at things binocularly, and they have to fixate first, and then they have supposed to find a uniquely oriented bar and staccato as quickly as possible. Okay, normally it takes them about 200 milliseconds before they can staccato it. However, they did not know ahead of time whether the bar should be here or there or somewhere else. So therefore, they have to find it first. Yeah. But in some trials, the bar happened to be in where we are recording from the neural activity. So therefore, you can record neural activity while the monkey do this experiment, do this task. And this is on the vertical axis, the neuron response against the time since the bar appear. As I said, usually it takes about 200 milliseconds before the saccade happen. And so this is before the saccade happen. And you can see that sometimes the neural response can be high, as in the red curve, and sometimes it's lower. And these are actually the same visual input across different trials. Now, what are they? When this trials giving higher response happen to be the trials when the saccade to the target is faster onset. And when it's slower response, the trials have a slower onset. So therefore, this difference in these two responses are completely related to behavior, not related to the visual input. And this behavior correlation is really, that means if V1 neuron is responding higher, you will get faster, more salient, faster saccade. And this is a saliency signal that happens at such a short latency that it is less likely it could happen by a feedback from higher visual areas such as V2 or V3 or V4, because these higher visual areas will have a later onset of their response. So there will Therefore, the feedback will take longer. Okay, and so therefore you can say, well, in that case, you're telling me V1 has a functional role that it's a motor cortex. So it sends a signal to a subcortical area to the brainstem and go to the muscle and move the eye. That is quite amazing, yeah? And in particular, let's look at the brain. And this is V1. It goes, you see that anatomically to superior colliculus. This is known a long time ago. But somehow, it could have given us a hint. In retrospect, that we could have already seen that. And superior colliculus then controls the eye muscles. But the brain has a big area. You can say, well, are you sure? So people then actually stimulate V1 electrically, and they find that at the stimulated location, you can elicit a saccade. Okay. And also, if you lesion V1, as I mentioned earlier, if you lesion V1, you see that retina also go to superior colliculus. So if you take V1 away, maybe the retina can also make saccade. No visually guided saccade for 2 months. Now, after 2 months, what happens? Well, the monkey recovers, and this leads to blind sight. And for instance, humans with blind sight, they have V1 lesion. They do not think they can see anything. They think they are completely blind, but they have some kind of ability, which is a little bit like a lower animals like mice. Yeah. So for example, mice actually use superior colliculus a lot to move to orient, but they can go without V1. So as if you don't have V1, you go to your evolutionary ancestral behavior. However, you can also, like the frontal eye field, also project to superior colliculus. If you lesion frontal eye field, traditionally, this is the area people thought to guide saccade. You find that monkey will wake up from the surgery, they immediately can do saccade, no problem. This is because you go to V1, go to superior colliculus, can still do saccade, yeah? And so therefore, this is quite a strong evidence showing that V1 is not just a sensory area, it is also a motor area for guiding saccade. And saccade is for attention. And for those of you who are interested in theoretical works, this is, especially if you're coming from, theory needs to predict something quantitative. These are qualitative prediction, which is already very much a fingerprint of V1. You can also predict quantitative. You can predict the distribution of reaction times for people to find a unique singletons like these. And you can find that your predicted quantity and the measured quantity fall on top of each other with no parameters to fit. It's not a fitting, it's complete match. And that gives us a strong confidence that V1 is actually guiding attention. Yeah. And you may say, well, you are having all these very simple stimuli. How about very complex stimuli? So for example, you can have unique orientation attracting gaze. Unique color can also attract gaze. Just like you can have ISA orientation suppression, you can have ISA color suppression. Here you have ISA eye of origin suppression. And you can also have two salient locations, just like here, you have two salient locations. And if this is more salient, they will attract attention. And you can also have the same bar that is unique both in color and orientation. Well, then this will attract attention even more than if it's unique only in color or only in orientation. This is because in V1, you have neurons tuned to both color and orientation. So for example, in this case, you can have this uniquely oriented bar put in a different eye. Now the observer will gaze saccade to this even faster because this bar is unique in eye of origin and orientation. And you can also have situations, in this case, you say, which one is more attracting attention? Is a bar among cross attracting attention more or cross among bars? Which one? The left or right one? Cross among bars, right? Well, V1 doesn't have a single neuron that's tuned to cross. How can this happen? Well, this is because this vertically oriented bar is being suppressed by ISA orientation suppression by neighboring bars tuned to vertical. So that's being suppressed. However, this horizontally oriented bars is the only one that escapes ISA orientation suppression. So therefore, this ISA orientation, this bar is evoking a higher V1 response tuned to the orientation horizontal. Yeah, and so therefore, you do not need V1 to have any neuron tuned to the cross to make your attention go to the cross. So therefore, you can have a face-attracted attention. V1 has no neuron tuned to the face. Yeah. So for example, you can have a situation where observers need to find a unique ellipse among circles or unique circle among ellipse. And it is found in visual psychophysics experiment that this people find it with a shorter reaction time than that. And you can make this ellipse out of many short bars, just like for V1 neurons can be activated, and you find a V1 model indeed give higher response to one of these bars. And so therefore, it is quite a complicated situation. And so we know that now V1, at least to some extent, it does attract your attention. So therefore, vision can be seen as something, first of all, you look. You look by shifting your gaze, therefore selecting a partial, a small fraction of all your input into your bottleneck. And this looking should happen before the bottleneck. Okay, so therefore before the seeing, because your brain has a limited capacity, it cannot see everything clearly such that to decide which one is more important for your survival. It doesn't have time for that. So therefore it has to decide where to look before you see. And this is an example where it looked before it could see, because it could not see that this is a right eye or left eye. So indeed it should do that. It's a little bit like having an egg without a chicken, before the chicken, yeah? It's like a chicken first or egg first, looking first or seeing first. We have impression as if we see this flower because we notice its red color. Well, this is a little bit of post-mortem rationalization, like, oh, hey, maybe because I see its unique color, that's I shift gaze. Or in this case, if you're not aware you're shifting gaze, you can look before you see, yeah? And then you see after the bottleneck. That's very interesting. Yeah, how can you do that? Okay, of course, you can also have top-down control. You say, well, once I know there's a flower, or maybe there is a person standing next to it enjoying the flower. So you may have a top-down control to do that. But for today, I'm not going to go to the top-down control. Just now, let's see what's the consequence on seeing, given that V1 has this functional role to guide your gaze. Is this a good point to pause again, Sebastian, maybe? Or anybody else like to maybe ask question, and you can just have a quick question and before the later. All right. Okay, if it's good, then I continue. If no question, I continue. Okay, so now let's look at seeing. Seeing is difficult by the bottleneck. That's the assumption, not the assumption. This is a logical consequence. So let's see. This is another example one can look more closely. Okay, now rather than letters, you fixate on this cross. You fixate on this cross. You can still see the letter T, right? No problem. But you cannot see that letter T, no? These two T's are equal distant from the cross. Okay, that means optically on your retina, even though on your retina you have many more cones in your fovea and fewer cones in the eccentric position. So therefore, the retinal cone density is the same on this T and on that T. However, if you fixate here, you cannot see that. That means the information on the retina is lost by the time you want to read that letter. However, if you fixate, put it in your central visual field, then you can see it, yeah? The reason is because in the central visual field, according to this framework, it can go back and fetch more information. Therefore, it can overcome crowding, okay? And this is assumption. This means not only you cannot see clearly, sometimes, so in this case, for instance, you say, I cannot see clearly, okay? So let's say, oh, I cannot see clearly. But sometimes you may see it wrong, okay? See it incorrectly. So it's not ambiguous, but incorrect. When you see something incorrectly, that's called illusion. Now, by this framework, that means in central vision, maybe you don't have illusion as easily as in peripheral vision because you cannot go back and fetch for more information. Shall we try some illusion for fun, yeah? Okay? Illusion in peripheral vision. Do you see some motion in this static image? Yeah. And this is something completely in your peripheral visual field. Try to focus at a particular location. If you stare at it, for example, you say, oh, it's moving. But if you stare at it, it's not moving. Because if you stare at it, it's in your central visual field. Okay? The moving part is always a little bit away from your gaze. So that means the illusory motion is vetoed in the central visual field because you can always go back and fetch for additional information. Okay? That's one example. Very strong, amazing. Here is another example. Do you see all the flashing discs? But if you stare at a disc, it doesn't flash. Yeah? Only the disc, you don't stare at the flashes. And so this is like, sometimes it's only very far away. But these two illusions were known in our vision science. We have collected in traditional vision lots of known illusions. And so therefore, they are not something predicted from my theory. It's just that once I had the theory, you look at these illusions, oh, now suddenly I realize actually if I stare at it, it doesn't happen. Okay? If I don't stare at it, it happens. So it would be a good idea. Can we not predict new illusions given we have this framework? It turns out that as far as I know, in traditional vision, there is no theory that can predict non-trivial illusions. So now let's look whether we can do that. Okay, so we are going to predict a new illusion. That's called reverse depth illusion. And I'll show you what it is, then I'll guide you how I predicted it. Yeah. So what is that illusion? This is actually looking at the depths. So in the 3D world, imagine you have a situation where you have a disk in front of the ring, and this disk and ring will give you two slightly different images in your two eyes. This is a schematic. This is the actual image you show to observers. And so therefore, for example, you have this black dot in one eye correspond to this black dot in the other eye. It will excite a V1 neuron, that a binocular V1 neuron whose receptive field for the left eye is for this dot, and the receptive field for the right eye is at this location. And this neuron is tuned to this pair of dots in the two eye, therefore say it's near depth. Now how it works, imagine you have two eyes, imagine you are staring at this dot. It's in your therefore, it's in your central visual field in both eyes, okay? So in both eyes, it is exactly in your central visual field. It has the same image location in two eyes, and then you can define a disparity, which is the location in the left eye minus its location in the right eye. In this case, it's equal to 0. And this will excite this binocular neuron tuned to 0 disparity. However, if you have this dot a bit closer, then it will have slightly different location in the two eyes. And so it will have a slightly different location. Now you have a non-zero disparity, another V1 neuron with this corresponding receptive field. In the left eye, receptive field is this location, right eye, this location will be activated. This neuron is tuned to the near depths. You can also, and such neurons are actually being activated by these dots, okay? And that's why you will see that, oh, this disk is in front, because V1 neuron is telling you this is near, okay? This is not an illusion, this is a baseline condition. You can also have a far dot, a dot further away than your fixation. Now the location of the dot in the two eye was slightly shifted the other way, and some other V1 neuron will be tuned to this other disparity, and these V1 neurons will be activated when the dot is far. So in V1, you not only have neuron tuned to orientation, you also have V1 neuron tuned to different depths. Okay, and sometimes it's the same V1 neuron tuned to orientation and to depths. So for example, this could be a V1 neuron tuned to a vertical orientation, yeah? A vertical black bar, or tuned to a vertical edge, white and black edge. Okay, so this is, okay, this is how V1 tells you this is a near depth and this disk is in front. That's no illusion. The illusion can happen if you modify the image a little bit, such that all you change is in the right eye image. Every black dot you make it white. Every white dot you make it become black, but the dot position do not change. Okay. Now this is called a contrast reversed random dot stereogram, so that a black dot in one eye for this disk correspond to a white dot in the other eye. Now, this is completely nonsense. However, a V1 neuron will be fooled. What happens is it has been observed that V1 neuron, this original neuron that respond to this pair of black dot, will no longer respond. But the neuron responding to this black-white nonsense pair is a neuron tuned to the far depths, not near depths, even though the disparity is still same. Let's try to understand how it works. So you will have one of the dot is now white, not black, yeah? So now this neuron, this is a receptor field, this is an off receptor field, therefore white and black cancel each other. So this neuron will no longer be activated. Does that make sense? Yeah, okay. Now what happens is you can put this black-white pair onto this neuron's receptor field. Well, this neuron receptor field, a black dot is here, a white dot is there. This neuron will be activated. This is how you cheat this V1 neuron. You just fool this V1 neuron, okay? Now the question is, so this is as if, no, that's not the question. So this is as if these V1 neurons are activating as if this disk is now behind the ring, okay? That means this V1 neuron is going to feed forward to V2 and V3, V4, telling them the disk is behind the ring, yeah? So the question is, what we human beings see this disk in front or behind, okay? And this was actually tested, people trying to have a look, and they say, well, this disk is neither in front nor behind. They could not tell. That's amazing. Now, what's the explanation? The explanation was V1 is not where consciousness is. Okay, this is, for instance, Francis Crick, Christoph Koch, they say V1 is not consciousness. So this seems to make sense, no? However, in our new framework, we say, well, actually, we have an alternative explanation. This is like you have a feed-forward input, because the reason is previously people look at it only in the central visual field. Well, in the central visual field, you have feed-forward visual input, and if it's in doubt, it will go back and fetch for more information. Now, what kind of more information it will fetch? It's the information that's not fed forward. Well, what kind of information that was not fed forward? The monocular information was not fed forward. So it can go back and ask, well, what is this dot? Oh, it's a black dot in the left eye, and go back and fetch for another information, the white dot in the other eye. Well, it could be one monocular neuron saying this is a black dot, another monocular neuron saying this is a white dot. However, there's a binocular neuron tell you this is a far dot. Now, these three neurons are nonsense. They are inconsistent. So therefore, the higher brain area with this reason say this is a fake news. This binocular neuron that originally tell me that the disk is behind is fake news. I don't believe it. Yeah? Okay, so this is the reason that you will just veto this information, and if you veto that information, you cannot see the disk behind. Yeah, now by this argument, it says that what if I do it in peripheral visual field where you do not have the ability to veto this illusion, yeah? And now you should be able to see exactly what V1 neuron tells you. Now, if V1 is indeed where consciousness is, then you should not see it. But if in our framework, you should see it. And that was tested and indeed confirmed in this experiment. And so, therefore, you should have a new explanation for this. This is because the new explanation is because central vision does not get fooled, but peripheral vision does. Okay, so do you like to try it? So if you have these glasses, if anybody has these glasses, you can try it. If you don't, I will give you an alternative. Okay, looks like nobody has this, at least the 9 people on the screen though. So I will just show you a different illusion. There's an analogous illusion in orientation. This is a second predicted illusion. So rather than looking depth perception, now we look at orientation perception. Okay, so you see this is a ring. This ring is made out of a lot of oriented elements. And these oriented elements are a pair of black dots, pair of white dots, just like in my stereogram, pair of black dots, pair of white dots, and these orientation perfect, yeah? Here you have some of these orientation perpendicular to the ring, so therefore destroy the continuity of the ring. And you will see this ring less well if I put it in noise. No? Do you see the left ring more clearly than the right? Yeah. So far, so good. This is baseline. Now, let's show you the illusion. I make a contrast reverse pair of dots. Okay, so the only thing happen is a pair of white. I just make it black, white, black, white. So every second pair is a black, white. And I'll tell you that you will see illusions if you don't stare at it. If you put the fixate on my red center, you will see it is the opposite orientation. Just like you see the opposite depths, you should see the opposite orientation. The reason is because the most activated V1 neuron is not its orientation, but the opposite one. The opposite one is 90 degrees away, yeah? And so that's why all of these things will give you opposite, every second pair of dots will activate a V1 neuron tuned to the opposite orientation. Now, if that's the case, if you put this in a noise, you will not see the ring as easily. Let's try it, yeah? Can you see it? The ring, not very easy. Right? Of course, then if you fixate in this cross, you just can't see the ring very easily. But if you look at directly in your central vision field, you can see it very well. So therefore, your central vision can do it. Now, to convince you a bit more, I'm going to show you another case. Now, let's first of all copy it to another image. But now I'm going to turn this into a perpendicular to the ring. Now, if you in your illusion, you see it 90 degrees away, it should now be parallel to the ring, yeah? Okay, so let's do every other one, just turn it to perpendicular. Okay, and so now it will activate V1 neuron as if it's all parallel, but here it's all perpendicular. So the question is, even though this is perpendicular, we should be able to see this ring more easily than this ring, even though it's all parallel. Shall we try it in a noise? Okay, which ring is more easily see if you fixate on the central cross? You can see the left one more easily, right? And so that means you all see this illusion. And this illusion is very much analogous to depths. In depths, you have pair of dots, black, black, white, white, you see true depth. But if it's black, white, you see fake depth in your peripheral. And if you still didn't see it, I'll give you something even more amazing. Do you see a ring rotating clockwise? Yeah? But this is an illusion. So if you fixate on one of its elements, you can see that it's actually going back, forth, back, forth, back, forth. It's not continuing going forward. Okay? This is because, in fact, it's 4 images cycling across each other. Okay? So it's like in the first time step, it goes from black to black. Second time step, from black to white. Third time step, black to black. And fourth time step, white to white, and then white to black. And so this is like the first step and third step, a true motion forward. The second and fourth step is fake motion forward. You just get fake news, yeah? And this is how it goes. So now let's see how we actually predicted it. So we know that from classical Hubel-Wiesel knowledge, orientation tuned neuron, this is an orientation tuned neuron tuned to horizontal, but you can activate it by a pair of dots that's vertical. Okay, and you can also see that this neuron normally is for horizontal things in its reciprocal field, whether it's a pair of white dots or a pair of black dots, or even a Gabor horizontal. But this, it can also activate, yeah? And so it could be all these 4 different inputs can activate. However, this vertical pair of dots does not activate another V1 neuron tuned to vertical. Now, if you let people see this vertical pair of dots, the most activated V1 neuron is horizontal. So far, everything is based on Hubel and Wiesel's classical discovery about how V1 neuron works. And so let me add a little bit icing on the top. So icing on the top is the bottleneck. So in V1, only one V1 neuron is fooled, but V1 has 100 million V1 neurons. And let's say the bottleneck only admit this V1 neuron into the bottleneck. So only this V1 neuron is sending information forward. Now, the higher visual area have knowledge that, okay, this V1 neuron maybe is V1 neuron number 13 out of 1 million neuron, 100 million neurons. and understood that this V1 neuron is sending 100 spikes to me, well, what could it be? It could be this possibility, all these possibilities could be. What is the possibility? That means based on this V1 neuron, you will have perceptual ambiguity. It could be all these possibilities. If you have to decide, you will have to make a majority vote. You say, what is orientation, vertical or horizontal? Well, 3 out of 4 possibilities says horizontal, 1 says vertical. You will say horizontal. That is the illusion. Yeah. However, if you say, well, there is a small chance it could be actually vertical, what you do is your higher brain area has an internal model of the world saying, what if this is the case? Well, you need to go find another V1 neuron whose response can distinguish these 4 possibilities. Not this V1 neuron whose response cannot distinguish. So for example, you should simulate what would be the would-be response from another V1 neuron to each of these 4 hypotheses about your visual world. Yeah, the perception is hypothesis. So you say, well, if I look at V1 neuron number 14, then it should be activated if it's the first possibility, but not activated for the second possibility and activated for the third and fourth. So therefore, the second possibility is now removed. You can look at another V1 neuron number 15, for example, and then say, okay, it should be activated, but not activated, and so on and so forth. So you keep looking, asking for more information until you can be sure it's the first possibility. And this process, it is called feed forward and feed back to query for more information, such as querying for the response of this neuron or that neuron, until you can verify each of the hypotheses and veto, reweight. Originally, this weight is 25%. You say, no, it's 0, 0, 0, and give this highest weight. And this way, you can then see the true image. And therefore, you have a difference between central and peripheral vision, because this is only available for central vision. It signifies visual understanding. Okay, and lots of people will say that is this predictive coding? It's not. It's paraphrasing a computation called analysis by synthesis. And so therefore, now we see how this works. But you should be critical about this, saying, well, it's like very beautiful story, but it's really so many elements in it. Can we have something simpler to explain it? A simpler alternative explanation for this observation is simply that the central visual field has higher acuity because it has more cones, has higher cortical magnification factor, and so on. So somehow that makes it less vulnerable to illusions. Okay, now that to test between these 2 alternative explanations, you need another prediction. And another prediction is that if you impair this feedback in central vision, then you should enable central vision to see the same illusion. Now, how do you impair that feedback? So we are going to use backward masking. So what we do is, imagine you have a feed forward and then feedback. Maybe feedback takes 20 milliseconds longer to come back, yeah? But what if when it comes back, you remove this visual input so it cannot get additional information? You should remove this input by a mask. That means you only show this for 20 milliseconds. Well, if it's 20 milliseconds, observers, difficult for them to see the depths. So what can we do? Instead, what we do is, after 20 milliseconds, I simply refresh all these random dots for the same disk, same ring, same dislocation, same ring location in both eyes. Its original is same, except the random dots are randomly regenerated with another random seed. That's all it matters. So that means when you want to go back and look up for this black dot and this white dot, when you go back, it's another dot. So you could not look up these dots. However, every random dot stereogram in one frame after another, they feed forward exactly the same depth information. Does that make sense? Yeah? Okay, very good to see you nodding. That give me very good feedback. And so this is how we do the experiment. You have observer press a button to start a trial. You show them this random dot stereogram. In this, you show them for 200 milliseconds. That's long enough for the feedback query to work. Now it's completely central vision. Okay, and then you mask it, and then you have to report whether the ring disc is in front or behind the ring. But you can also, this is a contrast matched random dot stereogram. You can also show them contrast and mismatched, reversed. Then this, they should see nonsense, okay, because they can have the feedback working. But you can also make dynamic random dot stereogram. That means every 10 milliseconds, you refresh the random dots without changing the disparity of the disk, without changing anything else, okay? Just refresh the random dots by randomly generating another independent sets of dots on the same disk and same ring. And you can also have anti-correlated contrast reversed ones. And then you find what happens. If you have these not a nonsense type of, contrast matched disks, you find that whether it's static or dynamic, this is the accuracy of the observers. One means they are 100% correct, okay? So observers, there's 13 observers, they can 100% correct. However, if it's contrast mismatched, when it is a static one, so their feedback is working, they are at chance level. So 0.5, because they can always have, press button one way or another, the 50% chance they can be correct. And this is completely at a chance level, yeah? Because the feedback is working, vetoing the fake news. However, when it's dynamic, the feedback is not working. Now they are even worse than chance. Now, what that means is when the disk is actually in front, there's 75% chance or 70% chance they say it's behind the ring. And when the disk is behind the ring, there's 70% chance that it's in front of the ring. So this is really the reverse steps. Yeah, okay. And since you don't have an antigraph, so I'm not going to show you. But since you're going to record it, I will show you, just have people who have it, They can look at this and they can, let me try that. You can actually see that I can make it dynamic. How do I make it dynamic? Maybe I don't do this. Let me do that. Yeah. Yeah, why did that not working? So I can do that. Do this. Okay. Do this. Okay, come on. That work? I don't know why it's not working. But don't worry, let's just proceed. So now let's summarize. What does V1 do? Well, it's like a motor cortex. A guide gates exogenous in order to guide your attention, okay? And then it feeds forward information, which this is the traditional view. V1 feed forward information to higher visual areas. However, different from the traditional view, it has to go through a bottleneck. So only a small fraction of information goes through to higher visual areas. And it also supports the feedback query. And there's alternative theories that says that, yeah, you need to do feedback in order for recognition. And they have another reason, they have alternative reason to say feedback. But in our framework, this feedback is only in the central visual field, and it's motivated by the fact that you have a bottleneck, you don't have enough information. So if you want more information, you have to go fetch for more. But if you have 100% information already here, well, you can then decode all the information by population decoding. You don't have to go back, yeah? So the fact that you have to feedback is because you don't have 100% of information, okay? And now with this framework, then we can better ask, because here we haven't quite said, is this V2 or V3 or V4? Now you can say, what if this is V2? What if this is V3, yeah? Of course, so far we haven't quite done the neural recording, but nevertheless, with this framework, neurophysiologists can follow up and do this and ask this question better. Imagine if you want to record reciprocal field here, it'll be a bit different from recording reciprocal field here because the information is already impoverished, yeah? And so therefore, when you study V2, V3, V4, you may even discover additional functional roles. So far, we have a functional role for gaze shift, and for this, and for that. We may have additional ones. Yeah? And so this framework to show us that knowing V1 can help us know additional about the brain, about the whole vision, and every theory needs to have these falsifiable, non-trivial predictions. And so far, these are only some of the predictions that are tested and confirmed. And so far, we haven't yet had a single prediction that is falsified. So, but however, there's some prediction not yet tested. So we still have chance to maybe falsify it because theory need more tests. In particular, one prediction, it says that this feedback is only for the central visual field. Turns out there's no data to explicitly say whether that's the case. So therefore, we may have a chance to test it. We have indirect data. For example, people have looked at the functional correlations between the central and peripheral V1 and the frontal cortical regions using Human Connectome Project. And in functional connectivity, which it's difficult to say whether it's a feed-forward information, feed-forward connection or feedback connection, or even whether it's monosynaptic connection or polysynaptic, you may have go to multiple stages. However, at least for the functional connectivity, it looks like the frontal area is more strongly connected to the central V1 rather than peripheral V1. So that's at least a partial but indirect support. And this is something interesting from monkey recordings in V1 and V4 simultaneously. And when you look at the receptive field of V1 and V4 in two electrodes that are overlapping for the same receptive field, you can analyze their correlations through some analysis called granular causality. And from the granular causality, they find that V4 to V1, sorry, there's a typo here, this should be just signals, is mainly on the fovea region. This is actually for monkeys spontaneously in the dark. So it will be nice to have non-spontaneous activities. And so therefore further tests are desired. And you may ask, is it possible by training such that the feedback can be even from the peripheral visual field? Yeah. So for example, when people are having macular degeneration that affects quite a lot of older people, their central vision is actually impaired. And then they cannot read, their function difficult. And it turns out that some people can go around their daily life better than others. Is that because they have training or not have training? Is there some training that can enable better feedback? They need to do that. Looks like this is something very interesting to investigate. And if they do, then you should find corresponding brain changes, and maybe they will see less illusions in the peripheral vision. So that's very interesting. Yeah, and that's a future study we could do. And so it turns out that a lot of these macular degenerated individuals, the training is really quite limited. It looks like the effect of training there is non-zero, but it's if you cannot read, it's really difficult to read. This is because our brain make peripheral vision is mainly for looking, it's for shifting your gaze. Okay, you can shift gaze with a whole V1. The whole V1 covers the whole visual field to guide your gaze by saliency before you recognize everything. Then central vision is where your spotlight, attentional spotlight, is for looking. So looking and seeing are two different roles specialized by peripheral vision and central vision, respectively. And one can then extend this framework regarding attentional shift and recognition for other animal species. Okay, so in particular, you might have animal species that doesn't have a fovea, but they also will have attentional bottleneck. The reason is the attentional bottleneck comes from your brain having limited resources. It cannot do everything, so it has to focus. So if our mighty human brain has this bottleneck, all other brains should have it. This bottleneck is caused by metabolism. We just cannot have all these ATPs to support. So in particular, it should be multisensory. So for instance, in primates, the central part is the visual fovea. That's where you actually fixate to the center of your bottleneck, attentional spotlight. The peripheral part that make you shift your gaze is not only your peripheral visual field, but also could be your auditory field that's behind you. It's not even covered by your visual field. Or could be somebody tap on your shoulder, you turn around, yeah? And so all these other senses can act to alert you, to make you shift your gaze, okay? So therefore, you can have a central field versus peripheral field. It's multisensory. But for other animal, for example, rodent, you can see, look at its orienting behavior. It doesn't shift gaze as much. It shifts its nostril, shifts its nose, okay? Because its central fovea is olfactory and microvibrissae, these whiskers near the nostril. And its peripheral is vision, okay? And so when you study mouse vision, it can give you a lot of information about how peripheral sense works. But we should be aware that it's qualitatively different from central sense. Just like we will have a lot of illusions in peripheral visual field, not in central visual field, we can study peripheral sense in our primates' peripheral vision or in the mice, yeah, vision. But we also have additional species like this one, artificial, has no bottleneck. So we humans, our brain is running on a power of 10 watts. But this can have a NVIDIA kilowatts. Your computer is really power hungry. So it can have lots of memory, a lot of processing power. Well, somehow it's still easily fooled, yeah? This means that it's not using its power as efficiently as we humans. You have heard about such things as adversarial attack. You can easily fool a current day robot, okay? Even though it doesn't have bottleneck as we do, but it's more or less still lacking a very good feedback query mechanism. And it's this feedback query that is the hallmark of human understanding. Because when you want to query whether it's a flower or an apple, you need to know what flower means and what apple means, what two pair of dots means, and this and that. Therefore, you can imagine and simulate what should be the V1 neuron's response if it's flower versus apple. This ability to query in this very specific manner is that you have an internal model of how a flower should look like, how a pair of black dots should look like, and pair of white dots should look like. And so therefore, you can extend this to think about, this is imagination. What if it's flower versus apple? What if it is discussing front versus back? You have a metaphorical thinking and this loop of going. You can even tell yourself stories with language and so on. So this is giving us a hope that understanding V1 is opening a window for us to understand vision. And understanding vision, here is a textbook I wrote if you're interested. Understanding vision, today I just started with a computational principle, functional role hypothesis, giving illusion predictions and behavior. We are yet to follow up with the neural basis, such as exactly how this will help us understand V2 and V3, V4. But now that we have a behavior task you can do, you can train monkey to do this task. Is the disk in front or behind? At the same time, you can measure the neural responses. And with that, we can use our vision as the window to our brain to understand all these higher order functions. And therefore, this is kind of using vision to see the brain and using human brain to see brains across species, therefore maybe seeing universal unifying principles. So thank you very much.
Thank you. So thank everybody that is still here. Thank everybody who was here. Was very nice for the first evening, I think. Thank you, especially Professor Zhaoping. Maybe we'll hear from you in the future again. Also, if you wanted to get more into the work of Professor Lee, you could go to her YouTube channel, you could go to her page, and you also could, of course, look up on Google Scholar or where her papers were published. And for us, that's it from our side. If you're not a member of our network right now, we would like you to join. Otherwise, you can share our network. And also, we're currently searching for new Leads members because there is a whole lot of organization behind some events like this, and there are more planned and currently going on. So if you would like to join, just write us a message, email us, and yeah, thank you for your attention and have a very nice evening.
And everybody's welcome to email me if there's additional question come up. Yeah, and I really enjoy talking with a group of people or motivated. Thank you very much.
Thank you very much.
Thank you so much.
Thank you.
Thank
Thank you.
Thank
Thank you.
you.